Well, I'm excited to announce our next speaker, Dr. Patrick Boyle. He leads the Cardiac Systems Stimulation Lab in the Bioengineering Department at the University of Washington. He uses computer models of the heart to cultivate new knowledge about heart rhythm disorders. We're very excited to hear from him today about bioengineering.
Thank you for the kind introduction, Brian. I am just making sure that everything displays properly. And thank you very much to Mayor for inviting me, for facilitating in advance of the lecture. So, is everyone seeing my screen? Okay, yeah, I will apologize in advance because, or I don't think I'm gonna, let's be optimistic. Let's not be pessimistic, but over time, Zoom has gotten worse and worse at showing slideshows, while especially heavyweight slideshows that tax the CPU. And so I've done what I can. This has been tested and tested, but there's always a possibility that things might freeze up. So like Brian told you, I'm an assistant prof here in Seattle at the University of Washington. And my lab focuses on the use of complex computational bioengineering tools to study the heart. So one of the things that we do is use information from pre-procedure MRI scans to help estimate risk of stroke. We're exploring emerging technologies like cardiac optogenetics, where we genetically encode ion channels or pumps that are light responsive instead of the normal voltage sensitivity or ligand sensitivity. We are working with Chuck Murray's lab at the Institute for Stem Cell and Regenerative Medicine to better understand side effects in the context of stem cell injection to help with heart attack recovery. And some of the most exciting work that we do focuses on what I like to call bespoke surgical procedures, where we take an MRI scan of a patient's heart, we load it onto the supercomputer and run thousands of simulations to try and determine the optimal treatment plan. And then we carry out the treatment based on those simulations. But in the context of today's meetings, I want to sort of subvert all of that. And I'm not going to talk about any of those projects because aside from being extremely cool, there's one thing that you might already have cottoned onto that all these studies have in common. They're very costly. They involve costly medical procedures, both the scanning and the intracardiac mapping and the treatment of the surgical treatments. Okay, so those are also costly. The computing resources are colossally expensive. We're really fortunate at the University of Washington to have access to an incredible supercomputing system called HIAC, but there's a cost associated with that we don't see. And I'm not going to go into great detail about it, but it's not just a financial cost; it's also an ecological cost. It's kind of glib and jocular to say we're melting the ice caps, but really, these supercomputing systems, are immensely taxing from an electrical standpoint, and so we have to think about that as a byproduct. And then the human resources associated with doing these simulation studies is also enormous. And so, this is where I'm hopefully, fingers crossed, not going to crash Zoom. It's kind of all about the Benjamins. And so in the context of global health and in terms of trying to use our research platform to make the world a more equitable, more just, and more inclusive place, a lot of these projects kind of come off sounding tone deaf, both to me and to the trainees who do them. And so one of the new frontiers that we're exploring is whether we can use artificial intelligence and machine learning. And yet another animation that successfully did not crash Zoom, so very happy about that. So the reason why this comes up is because we have these massive clinical data sets, and increasingly those are becoming freely available and easy to access and analyze. And then we have these extremely powerful tools for machine learning computation that are available for free, and they're relatively easy to implement. And we can potentially use those to circumvent the need for the costly clinical procedures, the costly surgical procedures, the costly computational time. If we can bypass all of those things, then maybe artificial intelligence and machine learning could offer a solution to our money problem. But there's a catch, and of course, there's always a catch. And it's that machine learning is far from perfect. And so I've got some examples here. This is one from the French medical system. It was a test for preeclampsia, and 4 in 5 cases in that system were false positives, which creates problems. You have Amazon's AI-driven human resources debacle, where they inadvertently created an algorithm that was basically biased against women. There are countless examples of artificial intelligence evangelists overpromising and under-delivering during the COVID response. And historically, for artificial intelligence in medicine in general. This fourth article I really like quotes Dr. Leo Anthony Celli, who is a principal scientist at MIT, and he says that he's actually grateful for the existence of the so-called valley of death between research and clinical application for AI-driven projects, because, as he puts it bluntly, we're just not ready for true AI-driven projects in medicine. And finally, here's the requisite dunking on ChatGPT. So this is from a couple months ago, but OpenAI is being sued by an Australian regional mayor because the ubiquitous chatbot has evidently been telling people that he was convicted for taking part in a foreign bribery scandal in the early 2000s while working for a subsidiary of the Reserve Bank of Australia, when in fact he was the whistleblower who had helped reveal that scandal. So think back to the Amazon hiring debacle, and let's contemplate the resources lost. And I'm showing this schematic here. We really like it's from a recent review. And it, part of why we like it is because it highlights the fact that we want to find a balance point. We don't just want to evangelize to the point that people overtrust computational tools like machine learning and artificial intelligence, but we want to try and strike that balance. But the focal point here for me is that in order to improve trust, in order to drive the line up from under trust, what we really need to do is increase transparency of these models. And our argument is that, in this, of all the things in this green box, that's low-key the most important one to try and achieve. And so, my thesis here, my premise of the talk is that computational bioengineering might be able to level the playing field by using emerging artificial intelligence and machine learning tools, but those tools need to be easy to understand, not just for the healthcare providers, but also critically for the patients themselves in terms of interpreting the results of an AI-driven test. And so I'm going to pivot now to talking a little bit about the medical part of this research, which is about a disease called atrial fibrillation. And so chances are there are about 100 people on this talk. Chances are there's someone on this talk who's experienced atrial fibrillation, or certainly there's people, including me, who have a loved one, in my case, my dad, who experience atrial fibrillation. It's the most prevalent sustained arrhythmia worldwide, and its prevalence, as the population is able to age more, as we live longer lives, more and more people are going to be in atrial fibrillation. And in fact, the prevalence is expected to rise 2.5-fold by 2050 from its current levels. Many patients also transition to a persistent form of the disease, which is a lot more difficult to treat and involves episodes of atrial fibrillation that last up to a week if left uninterrupted. So what is atrial fibrillation? Well, in a normal heartbeat, you have, and this is a nice animation that my PhD student, Savannah Bafoco, found for her defense from Medtronic. You have heartbeats that go from the upper chambers of the heart, the atria. The sinus node is located in the right atrium, and so excitation spreads through the atria and then aggregates at the atrioventricular node before entering the ventricles, and you get a normal contraction of the heart. In the context of atrial fibrillation, everything is kind of cattywampus in the atria. They're going a little bit spastic. They're not, the chambers themselves aren't contracting properly, and so blood can pool up and form clots in little tight corners of the atrium, and the ventricles still beat, but they beat irregularly. And so if and this might not come through perfectly over Zoom, if the normal heartbeat is a metronome at about 60 beats per minute, 50, 70 beats per minute, atrial fibrillation is characterized by these intermittent and irregular changes in the beat-to-beat interval. Okay, now I don't need you to understand a whole lot about the physiology or the pathophysiology of AFib in order to make it through the rest of this talk, but I want to point out that the pulmonary vein sleeves in the left atrium are an important source of the ectopic impulses that trigger atrial fibrillation. Okay, so I already mentioned that atrial fibrillation is associated with the formation of clots in the left atrium, and when those clots leave the heart, they can travel through the arterial system and end up causing a stroke. And so the clinical response to detection of atrial fibrillation tends to be anticoagulation with powerful medicines. And the clinical response to stroke is frequently, if it just happens out of the blue, like it did for my dad, the clinical response is to try to monitor for atrial fibrillation, try and look for signs of atrial fibrillation, and eventually, in many cases, we find it. Now, the current treatment goals tend to revolve around stroke prevention. Okay, so there are many different things that we can do to help prevent a stroke. We can manage comorbidities, so limit alcohol intake, lose some weight, stop smoking, treat your OSA, etc. But what I want to focus on is rate and rhythm control. So this is actually trying to alleviate the acceleration of the ventricular rate that can happen in consequence of atrial fibrillation, or to go in and intervene surgically with a procedure called ablation, catheter ablation, highlighted in the bottom part of this slide, in order to surround the left pulmonary vein sleeves that I mentioned earlier. This is why I pointed it out so that you can understand this, by basically inducing scar tissue. So we use radio frequency energy that causes local heating of the tissue, and the tissue forms scar. And then those ectopic impulses I mentioned that tend to initiate inside the pulmonary sleeves, they can no longer get to the meat of the atrium, and they can no longer cause it to fibrillate. Okay, so relatively routine clinical procedure. There were probably 4 or 5 of them at least that happened at UW Medical Center this week, if not a few more. And so taking into account the totality of that, let's ask the question, how can computational bioengineers help? So we know that long-term ablation success rates are relatively low. And we also know that predicting procedure failure is difficult. So once someone has had the ablation, it's sometimes difficult for them to know, like, well, did it work? You know, am I going to be back in here in 6 months or a year getting another ablation or getting a different treatment? Can I go off my anticoagulants? Do I still have to take this antiarrhythmic drug that has some gnarly side effects? Okay, so that's kind of the landscape of the problem. And what we know from the decades of research is that there's a relationship between fibrotic remodeling. And so this is the sort of stiffening, and so the meat gets tough in the atria, and we can reveal those patterns of fibrotic remodeling in the atria using a particular type of magnetic resonance imaging, using gadolinium as a contrast agent. And we know that the drivers that sustain AFib, which are these sort of vortices of electrophysiological activity shown in the bottom right corner of the slide, we know that those are associated with increased amounts of atrial fibrosis. And so if a patient has been characterized with the MRI, we can use computational models to better understand how to treat them. But again, that is super expensive, okay, in a variety of different ways. And so the question I pose here is, can we use instead cutting edge explainable machine learning approaches to tackle this problem? The sort of requisite plug, though, for the computationally intensive stuff is here from our 2019 paper, which was published in Nature Biomedical Engineering. But again, not going to talk about that today. Instead, let's pivot to talking about explainable machine learning. And so there's a whole bunch of information on this slide and a whole bunch of different logos for the various different technological platforms that have been developed by others, not by us, but that are sort of plug and play, ready to go to help increase the interpretability and explainability of the artificial intelligence prediction and characterization algorithms that are out there. And the one that we're going to focus on is called SHAP, which stands for Shapely Additive Polynomials. And it was actually developed by Sue-Lin Lee, a computer science professor, and her team at University of Washington. And so my wonderful PhD, no longer candidate, now Dr. Savannah Bofoco, because she defended last month. So the way that she explains SHAP, not only to the audiences that she talks to, but to me, her machine learning skeptical PI, she says, think about model features like players in a game. And so when we have machine learning algorithms, we're going to plug in a bunch of features and we're going to ask it to spit out an outcome. So if I give it the black box a ton of information about an individual patient, the purpose of the exercise is to say, do I think this patient is going to have a recurrence after their ablation procedure or not, for example. So if the features are the players, then SHAP helps us characterize the extent to which each player is contributing to the outcome of the game. And in this case, the game is the idea of the prediction, yes or no, this patient will recur. Okay, so let's look at an analogy from my favorite pastime, which is complaining about professional hockey. I didn't mention this beforehand, but I should disclose that I am a Canadian and I am a shameless Calgary Flames fan, despite the fact that they're a terrible hockey team. So in this example, what we're going to look at is what's the incremental value of adding a player to the lineup in a given game. And the analysis, the outcome that we're going to look at with SHAP will be, will we win or will we lose? All right. So we've got Nazem Kadri, outstanding player, good Toronto boy, and he's really pulling his weight. So he's adding likelihood to our win. If we have him in the lineup, we're 12% more likely to win. And then we've got our boy Mackenzie Weegar, recent acquisition, came up from Florida. You know, he's acquitted himself quite nicely. Plus 0.8%, not bad for a stay-at-home defenseman. And then you've got Chris Tanev, fan favorite because of the mugshot, but not really pulling his weight. And we've got Milan Lucic, now plays for the Boston Bruins. Can't say I'm too unhappy about that. So there are 5 skaters on a hockey team. Let's add the 5th one. Let's add me. Oh, okay. So I'm terrible at hockey, despite my Canadian upbringing. I can barely skate, and let alone skate backwards. And so when I'm on the ice, it reduces our likelihood of winning by 800%. We're going to lose badly every time. Now, what if we instead add my brother Brendan? Okay, he's better than I am, and so maybe we win. Okay, so this is the concept of SHAP, and I'm going to show you in the remainder of the slides here how that works in the context of predicting outcomes of catheter ablation procedures. So the question that we want to answer for the patient, not just for the clinical care team, is, I just had a catheter ablation. I'm feeling a lot better. Is this feeling going to last? And so we have a huge number of features which constitute the players of the game. So these are information from electronic health records, information from the MRI scans, about scar induced by ablation, about the existing fibrotic substrate that was there before the procedure. We have the geometry of the atria before and after the procedure. And then the outcome of the game is, can we predict whether the patient is going to have a recurrence? The specific features, there are way too many to go over individually. Let's sort of, the usual suspects: persistent or paroxysmal atrial fibrillation, what kind of ablation, age, sex, symptom severity, hypertension, and so on. And then again, we have fibrosis features based on prior computational modeling work. We have region-wise distributions of fibrosis or scar in the left atrium. We have proarrhythmic ablation scar features that I'm not talking about this in this lecture, but we did an earlier SHAP study that identified really specific types of ablation scar that we think could be detrimental instead of being therapeutic. And then we also, in some cases, have locations of simulated atrial fibrillation drivers from patient-specific simulations of these models, although in the current analysis, we've removed that in the interest of trying to make this more accessible. Our main collaborator on this project is Dr. Nazem Akoum, and what he wanted to say, I have to sort of advertise this, is that we can't use all of these features because that doesn't make sense in the context of a big machine learning model. So we use lasso regression, which is a parameter reduction technique, to select the most salient features. All right, so how did we do? Not bad. So our area under the curve, which is generally speaking a decent measurement of predictive value. We've got some other measurements like precision recall that also show good values, but it's about 85%, 0.85. And so we're in pretty good territory in terms of the predictive power of the model itself. And it's comparable to the competition. in different groups who are seeing similar numbers.
Come back. It just depends on who you want to listen to talk.
Okay, I'm hearing some audio in my headphones, but I'll just keep going. But much more exciting than the predictive power of the model itself are the rank ordered feature list of these that's produced by the Shapley analysis. Okay, and so what we can see on this slide is that there's a sort of, there's a decent number of features that are highly predictive of ablation recurrence or highly predictive of the lack of recurrence. And that's shown down here on the sort of x-axis, far left versus far right. But where I think these models really shine, and I'm going to skip over this slide, which just sort of shows the same type of thing for two of our key driver features, the post-ablation size of the atrium and the number of ablation lesions that were delivered, is that we can now do these individual snapshots. So instead of just looking at the data in aggregate in something like a receiver operator characteristic curve, we can now do an individual patient-specific breakdown of when the model said, yes, I think this person is likely to not recur. It's going to show its work. It's going to tell us, and here's why. And so, for example, in this case, the most important predictive feature, as I talked about in the previous slide, was post-ablation left atrial volume index. But if we were to take that post-ablation left atrial volume index into account alone for a patient like this individual, we would make the wrong decision, okay? Because there's a preponderance of other factors drawing it in the other direction. So wrapping up, what we think is that there are incredible potential applications of explainable machine learning in the context of trying to predict arrhythmia and recurrence. We think that it could be used as a tool for ablation planning, for post-ablation care, to inform new hypothesis-driven research. And really, the one that I want to emphasize is to facilitate better communication between patients and the healthcare providers who look after them. Okay, because if you tell someone, I think there's an X% likelihood that this procedure has worked, that's kind of opaque. It's really unsatisfying from a patient standpoint to hear that. And we think, sort of the underlying hypothesis of this work is that we think that it would be more reassuring to be able to tell them, and here's why. So in conclusion, I'll try to give you my illustration, or my answer to this question. Is explainable machine learning hype, or is there hope from this to deliver, as part of a system of using our research to deliver a more just and equitable world in the context of the existing healthcare system? And we do think that explainable machine learning can be super helpful for shedding light on complex recurrence mechanisms in atrial fibrillation. Their apparent drivers of recurrence vary dramatically from patient to patient, and the explainable machine learning tools can really help us parse that with remarkable granularity. Now, applying explainable machine learning, in our opinion, to existing data could potentially reduce the need for these extremely costly computational simulations, which is literally in the name of my lab, but here we are. However, I would point out that we still have very expensive and inaccessible procedures that are part of the information we need to give to the machine learning in order to make this work, namely the MRI procedures themselves. So we're still working on that, but potentially we'll get there using things like analysis of a garden variety electrocardiogram and ECG. So my answer is that maybe there's hype and hope. All right, so that's the end of my lecture. I want to thank the people who did this, especially the ones that I'm going to highlight in this animation, particularly Dr. Bafoko, Dr. Masharet, our wonderful undergraduate student, Izzy Kim, Nazim Akoum, our primary collaborator, UW Medicine, and a brilliant research fellow who's now doing his residency at UW, Dr. Yaqub Shaheen.
What's interesting.
Just laugh.
Okay.
Thank you
Any
so
questions?
much, Dr. Boyle. This was, I just want to say this was really amazing, and it was really, it was such an interdisciplinary approach, really nicely put together, and I think it's just such cutting edge research, which makes it all the more fascinating. So it's also so nice to see how you incorporate AI into your work as well.
Thank you.
So yes, thank you so much, Dr. Boyle. We really appreciate your time today. And